stand at the base of the Great Pyramid of Giza, and you're confronted with something that defies comfortable explanation. 2.5 million limestone blocks, some weighing as much as 70 tons, stacked with such precision that you can't slip a piece of paper between the joints. And here's what should trouble you. This wasn't built with cranes, steel cables, or computer-aided design. This was supposedly accomplished over 4,000 years ago by a civilization using copper tools and wooden sledges. The mathematics embedded in its dimensions encode pi and the golden ratio. Its alignment with true north is more accurate than the Greenwich Observatory, built thousands of years later. The internal chambers contain granite blocks transported 500 miles and lifted 200 feet into the air with tolerances measured in fractions of an inch. When you actually calculate the engineering requirements, the precision, the logistics, the astronomical knowledge, something doesn't add up. Not because ancient Egyptians weren't brilliant, but because what we're looking at suggests capabilities that shouldn't exist in the Bronze Age. So let's do what physicists do best: follow the evidence wherever it leads, even when it challenges everything we thought we knew about human history and the limits of ancient technology. Let me begin by saying something that might surprise you. I'm a physicist, not an archaeologist. My training is in the mathematics of space-time, the curvature of the universe, the strange behavior of quantum fields. So why would someone like me be talking about the pyramids? Because when you strip away the mysticism, the sensationalism, the conspiracy theories, what you're left with is a problem that demands the kind of rigorous analysis we apply to any mystery in nature. And the pyramid problem, when you examine it closely, presents us with a series of contradictions that are difficult to reconcile with our current understanding of Bronze Age technology and human capability. Let's start with something concrete, something measurable. The Great Pyramid contains approximately 2.3 million stone blocks. The accepted timeline suggests it was built over a period of about 20 years during the reign of Pharaoh Khufu. Now let's do some basic arithmetic, the kind I do with my physics students all the time. 20 years is roughly 7,300 days. If we assume they worked every single day without exception, no rest days, no festivals, no seasonal interruptions due to Nile flooding, they would need to place approximately 315 blocks per day. But let's be more realistic. Ancient Egyptian laborers certainly had rest days, religious observances, and couldn't work during the flood season when the Nile overflowed its banks. If we account for a more reasonable work schedule, we're looking at maybe 250 working days per year. That changes our calculation dramatically. Now we're talking about placing, positioning, and securing roughly 460 blocks every single day. That's one block every 2 minutes during a 12-hour workday, or one block every 90 seconds if they worked 16-hour days. But here's where it gets even more challenging. These aren't uniform blocks we're talking about. Some weigh 2 tons, others 15 tons, and the massive granite blocks in the King's Chamber weigh up to 70 tons each. 70 tons. That's approximately 140,000 pounds, equivalent to about 12 full-grown African elephants or 18 average cars, and these granite monoliths weren't quarried nearby. The nearest granite source is Aswan, approximately 500 miles south of Giza. Think about that journey for a moment. 500 miles through a landscape that, while following the Nile, still presents enormous logistical challenges. The conventional explanation suggests they floated these blocks on barges during the flood season. That's plausible for transport, certainly. But then you have to get them from the Nile to the construction site, and more importantly, you have to lift them 200 feet into the air and maneuver them into chambers with ceiling clearances measured in inches. The precision is what haunts me most. I spend my days working with equations that must be precise to multiple decimal places to accurately describe the behavior of particles and forces. Precision matters. and the precision demonstrated in the Great Pyramid is extraordinary by any standard. The base of the pyramid is level to within 2.1 centimeters over a base spanning 13 acres, 2 centimeters across 13 acres. To put that in perspective, that's more level than most modern concrete foundations. The 4 sides of the base align with the cardinal directions, north, south, east, west, with an accuracy of 1/15 of a single degree. The deviation is so minimal that the pyramid is more accurately aligned with true north than the Royal Observatory at Greenwich, which was built with telescopes and precision instruments in the 17th century. When I discuss quantum mechanics with students, I often talk about how measurements at the smallest scales require incredible precision. The pyramid builders achieved similar precision at the largest of scales. The ratio of the pyramid's perimeter to its height is 2 pi, encoding the mathematical constant that describes the relationship between a circle's circumference and its radius. Whether this was intentional or coincidental is debated, but what's not debatable is that it's there, precise to several decimal places. The internal chambers incorporate the golden ratio, phi, approximately 1.618, a proportion that appears throughout nature and has been used in art and architecture for millennia. But again, this is supposedly a structure built by a civilization that, according to conventional timelines, was still developing basic arithmetic. Now let's talk about the internal architecture, because this is where the engineering becomes truly perplexing. The Grand Gallery is an ascending corridor that rises at a 26-degree angle for over 150 feet. Its corbelled ceiling, where each successive layer of stone projects slightly inward from the layer below, rises to a height of nearly 30 feet. The precision required to construct this without collapse to ensure that the weight distribution doesn't create failure points requires sophisticated understanding of structural engineering principles. Then there are the so-called relieving chambers above the king's chamber. These are 5 separate compartments built with massive granite beams, each weighing 40 to 70 tons, designed to redistribute the enormous weight of the masonry above away from the burial chamber ceiling. The engineering principle here is sound. It's essentially what we might call a primitive stress distribution system, but the execution requires knowledge of load-bearing calculations, material stress limits, and structural mechanics that we typically associate with much later periods of human development. The tool problem presents another layer of mystery. The copper tools available to the ancient Egyptians were relatively soft compared to the materials they were supposedly cutting. Copper has a Mohs hardness of about 3. Limestone, the primary material of the pyramid's body, has a hardness of 3 to 4, so copper tools could theoretically work the limestone, though inefficiently. But granite has a hardness of 6 to 7 on the Mohs scale, and the granite used in the Great Pyramid contains quartz crystals, which rate a 7. You cannot efficiently cut a harder material with a softer tool. It's a basic principle of materials science. The conventional explanation involves copper saws used with quartz sand as an abrasive. While this is technically possible, experimental archaeology has shown that this method is extraordinarily slow and requires constant replacement of copper tools. When you calculate the number of granite blocks used and the surface area that would need to be cut and dressed, the numbers become staggering. You'd need thousands upon thousands of copper tools, all being worn down and replaced on a continuous basis, requiring a supply chain for copper that would rival the pyramid construction itself. There's also the matter of the internal passages and shafts, the so-called air shafts that extend from the king's and queen's chambers are only 8 inches square, yet they run for over 200 feet through solid masonry at precise angles. One set aligns with the constellation Orion, another with the star Thuban, which was the North Star in ancient times due to the precession of Earth's axis. This astronomical knowledge, understanding not just where the stars are now, but where they were thousands of years ago, suggests a sophisticated grasp of celestial mechanics. As someone who studies cosmology, I can tell you that tracking stellar positions over long time scales and understanding axial precession requires mathematical modeling and sustained astronomical observation over generations. Let me take you deeper into the mathematical mystery. The pyramid's dimensions encode relationships that seem too precise to be accidental. The height of the pyramid multiplied by 10 to the 9th power approximately equals the distance from Earth to the Sun. The pyramid's weight, when calculated, is estimated to be approximately 5.9 million tons, which happens to be the estimated weight of the landmass of the Nile Delta. The perimeter of the base divided by twice the height gives you pi. The slope angle of 51.8 degrees is a natural consequence of using the golden ratio in the design, specifically creating a triangle where the ratio of the slant height to half the base equals phi. These mathematical relationships might be coincidental, but when you pile coincidence upon coincidence upon coincidence, at what point does the probability become so small that we have to consider alternative explanations? The acoustic properties of the King's Chamber have been studied and reveal something unexpected. The chamber resonates at a specific frequency, approximately 117 Hertz, which some researchers have noted is close to frequencies used in certain meditation practices and sound healing. The granite used in the chamber contains high concentrations of quartz crystal, which has piezoelectric properties, meaning it can convert mechanical stress into electrical charge and vice versa. Whether this was understood or utilized by the builders is unknown, but it represents another layer of sophistication that seems anomalous for the time period. When we look at the broader context of Egyptian civilization, we see something puzzling. The pyramid building era represents a sudden peak in construction sophistication. Earlier Egyptian structures were mud brick mastabas, essentially rectangular tombs with sloping sides. Then, seemingly abruptly, we get the step pyramid of Djoser, followed less than a century later by the Great Pyramid, which represents a quantum leap in engineering, precision, and scale. And here's what's truly odd. Pyramid construction quality declined after the 4th dynasty. Later pyramids were smaller, less precisely constructed, and many have collapsed over time, while the Great Pyramid stands essentially intact after 4.5 millennia. In physics, when we see a sudden peak in capability followed by decline, we usually suspect that knowledge was lost, borrowed, or incompletely understood by those who came after. The quarrying itself presents problems that are rarely discussed in detail. To extract a 2-ton limestone block from bedrock using Bronze Age technology, workers would theoretically chisel or pound channels around the block, then use wooden wedges soaked in water that expand to crack the stone free. This is plausible, but incredibly labor-intensive. For the granite, the process is even more difficult. Some blocks show evidence of what appear to be drill cores, cylindrical holes that seem to have been made by tubular drills. The spiral grooves inside these drill holes suggest a drilling rate that's difficult to explain with the soft copper tools available. Experiments by engineer Christopher Dunn have shown that to achieve the drilling rates evident in some granite cores would require a ton of downward pressure and rotational speeds that are challenging to achieve with manual labor and primitive tools. The transport mechanisms are equally mysterious. Moving blocks across the desert sand would be impossible without some kind of trackway. The theory suggests wooden sledges pulled by large teams of workers on tracks wetted with water to reduce friction. This is plausible and has been demonstrated experimentally on a small scale, but scaling it up to move 70-ton blocks raises serious questions about the structural integrity of wooden sledges and the coordination required for hundreds of workers pulling in unison. And then there's the ramp problem. To raise blocks 280 feet high, you need ramps. But what kind of ramps? Straight ramps extending outward would need to be over a mile long to maintain a usable gradient, and the volume of material in such ramps would exceed the volume of the pyramid itself. Spiral ramps wrapped around the pyramid's exterior are more compact, but present problems with turning corners while pulling multi-ton loads. Internal ramps have been theorized, but archaeological evidence for them is limited and disputed. Some researchers have pointed to the work gangs markings found inside the pyramid, hieroglyphic graffiti that includes the name of Khufu and names of work crews. These are offered as definitive proof of the pyramid's conventional timeline and construction. But here's the thing about evidence. It tells us that people were present during construction or modification, not necessarily that they possessed the technological means to achieve what we see. If you discovered my name carved inside a modern smartphone factory, it wouldn't mean I understand semiconductor fabrication or could personally manufacture microchips. Presence doesn't equal capability. What troubles me most as a scientist is the absence of developmental stages. When we trace the evolution of any technology, whether it's writing systems, metallurgy, mathematical notation, or architectural techniques, we see a progression. We see trial and error, improvements over time, occasional regressions, and gradual refinement. The pyramids appear to violate this pattern. The engineering sophistication seems to arrive nearly fully formed, and then, inexplicably, the knowledge appears to fade. Later dynasties couldn't replicate what the Fourth Dynasty achieved despite having more advanced tools, more developed writing systems, and accumulated knowledge. It's as if the Fourth Dynasty had access to expertise that subsequent generations lost or never fully possessed. I want to be clear about something. I'm not suggesting aliens built the pyramids. That explanation simply replaces one mystery with a larger one and provides no testable hypotheses. But I am suggesting that our timeline of human technological development might be incomplete. There might have been earlier, more sophisticated civilizations whose knowledge was partially preserved and transmitted to the Egyptians. There might have been technologies or techniques that have been lost to time because they weren't recorded in ways that survived. The archaeological record is fragmentary. We're looking at tiny fragments of material culture and trying to reconstruct entire civilizations. It's like trying to understand modern civilization from scattered iPhone components and a few Instagram posts surviving 5,000 years into the future. The Great Pyramid stands as a challenge to our assumptions about history, about human capability, and about the linear progression of technology. As a physicist, I've learned that when observations don't match theory, it's the theory that must change, not the observations. The pyramid is an observation, solid, measurable, undeniable. Our theories about how it was built, when it was built, and what technological capabilities existed at the time might need revision. That's not pseudoscience or conspiracy thinking. That's the scientific method. We observe, we measure, we calculate, and when the numbers don't add up, we admit uncertainty and keep searching for better explanations. The pyramids are telling us something about our past that we haven't fully heard yet, and perhaps the most scientific thing we can do is acknowledge what we don't know.